All right, 10 a.m. again. Good morning, Calgary. Let me know if you can see and hear me. That would be great. All right. How is everybody? Week 5, day 1. Did you realize when you signed up that you were going to be here on statutory holidays? Awesome. Thank you, Andre and Sam. Perfect. Okay. Week 5. Already. Yeah. Any thoughts, any feelings on getting into this week? The weekend readings? Nothing? All right. Why don't we jump right into it? This entire week is about databases. This is not something that we used to do in the week 10 curriculum. We used to spend one day on databases. So I'm very happy that we've expanded to an entire week for this. So to get started, pretty much 100% of today is going to be on so-called select statements. And we'll get more into what those are. But before you get into the idea of designing databases, we're going to cover retrieving information from databases first. So why don't we start off with what is a database? And why do we need them? Let's start with that. Let's start with the need first. So what happened in TinyApp and in Tweeter when you restarted your server? All your data was gone, right? You were all the way back to whatever your initial seed data was, right? 2 tweets or 2 initial URLs, whatever it was, if you had anything. So we've identified the need to persist data beyond the lifespan of the server, right? We need to have some way of storing data that the server shuts down, starts back up again. Maybe we have multiple servers running because our app is so successful that one server can't handle every single request. So we need to have our data somehow persist beyond the lifespan of the server, which means external to the server, right? That's the only way that we can have data persist. Because obviously if it's inside the server, when the server restarts, when the server shuts down, when the server crashes, everything's gone, right? And that's clearly not what you see with like Facebook or Twitter or Gmail or whatever. When your browser shuts down, if the server has a crash or something, do you lose all your emails? Obviously not, right? Cool. So what are some options besides the D word? What are some options for us to persist data? What have you already used? Saving files. Exactly. We could just write to like a TXT file, right? Or if you've used Excel in the past, how was the font size? Is that good? Awesome. If you've used like Excel in the past, that's actually a CSV file, a comma separated values file. So everything in there looks like value 1, value 2, etc. Comma separated values. Why wouldn't we want to use something like this? Why wouldn't we want to just write to a file on our file system? Just have the server say, okay, I got a new tweet, add that to this tweets.txt and move on, or tweets.json and move on. And then the next time someone makes a request, well, we just read that file into the memory and serve it back up again. Why would this be not so good? And it might not yet be evident because almost every single app that you've built has had one user, right? It's just you testing locally on your own machine. But if we scaled that out, you might have noticed through your different read files, write files exercises, mostly just read file, right? When you read from a file, you actually lock that file. Your server has to sit there and read in that information. And if someone was trying to write and read at the same time, then you're hitting these lock issues Where, have you ever tried to edit a shared Excel file that's stored like locally on a network? And what do you see? You see this file is locked for editing by X user. You can only open it in read mode, right? So great. So you can read the data, but you can't update anything until that other user lets go of that lock. Because what happens if I'm trying to write to a tweet and you're trying to write to the same tweet at the same time? Whose write is going to take, right? But if we have a file system like this, whoever opened it first, that's it. It's first come, first serve, right? We obviously know that we can't persist in volatile memory, right? Which was what we were doing, which is the server memory, because obviously that shuts down. So that leads us to the D word, databases. Okay, so what is, that brings us back to the original question. So is everyone clear on why we need to use a database and why we're spending an entire week teaching you about databases? Okay, cool. So what is a database? In broad terms or specific terms or Calgary terms, hint, hint, anything. Tables. Tables. I like tables. Awesome. Could we say something like a collection of tables? Awesome. There we go. So we've established that a database is a collection of tables. What is a table? It is. It's a collection of columns and rows. Awesome. Let's see if we can. This is going to go very wrong. How about data table? There we go. Awesome. Ooh, oh, there we go. Great. Table. Done. Okay. Is it noon yet? Okay. Not quite. So as we can see here, as you're probably all intimately aware if you've used anything like Excel or Calc, this is a table. So we have our columns and our rows. So each row here, so if we look at number 2, USA, Fuller, each row in a database is referred to as a record. Okay? So this is one complete record. All of this data is related to some entity, some user or some salesperson, some contract, some order, something like that. Everything laterally is connected together in some way. It's related data. And each of these columns that run north-south here or up and down here, is a piece of information about that. We can think of that like, there we go. We can think of that like props on an object. So if column or row 2 here, I'm pointing at my screen so you can all see it. If row 2 here was an object in memory, let's say, then it would have a prop called country and a value of USA, a prop called salesperson and a value of Fuller, yada yada. Okay, so the big takeaway from this: rows are referred to as records, columns are referred to as fields, and you can think of fields as properties on an object, some adjective that describes that particular thing, whatever it is. So let's jump over here and we say rows are referred to as records, and a record is an individual instance of whatever the table is storing. And that might be a little vague, but let's say, so one user in the users table, something like that. Okay, and columns are referred to as fields. There we go. Okay, so that leads us to, okay, so in a nutshell, a database is a collection of tables. Tables look like this. We'll get into the relational portion later. But for right now, let's assume that all of the data in this table is also related to each other piece in some way. Like These could be all of our sales orders. It could be all of our users. Something like that. The nature of a database is that everything is structured in a certain way. If we liken it to an array, then in an array you might have an object, and then your next entry might be a Boolean value, and your next entry might be an integer, something like that. Like, these are not necessarily related in some way, right? So we can think about it more like if you had all of your users together, A, B, what is the Bob? There we go. And Carol. There we go, the old ABC. Awesome. So kind of the way that you got to with TinyApp in the end is you had a whole bunch of objects in memory, but they all had the exact same structure, right? You could safely look inside them and say, what is your short URL? What is your long URL? Which user ID are you associated with, right? They all conform to the same structure. And that's, as you can agree by looking at this table, all of the data in that conforms to the same structure. Every single record has a salesperson associated with it, and an order date, and an order ID. And they don't have extra columns. None of them have, like, also has dogs or something like that, or friends or something. It's not, all of the data conforms to the exact same structure. Can we agree on that? Cool. I'll come back to arrays quite a bit because there's a bunch of different operations that we perform on arrays that we will be performing through making queries to our database later. Cool. Okay, so this is awesome, but we're not actually going to interact with the databases directly. We're going to go through something called an RDBMS, which sounds like something that should have come from, like, the Princess Bride, right? Thank you. One laugh. Awesome. Is anyone familiar with the ROUSs? Rodents of unusual size. Okay, you can Google that later. Great. So we are actually going to deal with a relational database management system. So this is actually what we're going to deal with. And this is simply a special server that accepts requests for data from/to a database. So RDBMSs are the equivalent of web servers, but for databases. And this is how we're actually going to communicate with the database. We're not actually going to talk to it directly. We're going to talk through an interface, and we're going to say, I have a request from this database, from this table, give me back all of the records. And the RDBMS is going to say, okay, I'll take care of that for you. And then it's going to give us back the information. This is a completely separate application running somewhere. For the purposes of Lighthouse, you're going to have your RDBMS is running on your Vagrant machine. And they actually start up automatically when you do Vagrant up. You actually have two RDBMSs running on your Vagrant machine, believe it or not, because we haven't upgraded the Vagrant from when we used to teach Mongo. So you also have a Mongo server running on your Vagrant every time you start it up. But in particular, you have a Postgres server running, which you will access with the command PSQL to take you into a REPL, right? Where you can actually communicate directly with it, right? Cool, and we'll introduce on Wednesday a way of programmatically interacting with that RDBMS, with that database server. Because these first 2 days, today is going to teach you how to retrieve data, tomorrow will teach you how to design databases, and Wednesday will teach you how to take the JavaScript that you know and your new database knowledge and mesh them together so that you can have dynamic websites pulling information from databases. Yay. And then for the rest of the course, that's what you're going to do. Cool. Especially midterms. Yay. Starts on Friday. Awesome. Okay, so I hope this is clear that this is a completely separate process that's running from your server. So now we have actually entered into, we have our client, which communicates over HTTP/TCP. I didn't get to give you that lecture, so I didn't get to bore you to tears that day. So this is probably the last lecture I'll give you, so I'll bore you to tears today. This is going to be awesome. Then it communicated with our web server, right? And requests and responses went back and forth. Well, we're going to introduce a new entity, which is our RDBMS. And we're going to communicate with that using, in our particular instance, the Postgres protocol, which also works over TCP. So if you recall from that lecture, what does HTTP do? It converts your data into ones and zeros, but in a particular way, right? It gives everything like a header and an origin and a destination, and it encodes your data in a specific way. Well, that's all this protocol does as well, is it encodes your data in a specific way that the RDBMS knows how to read. That's all it is, okay? So we're just introduced a whole new player to the game that sits external to your web server and that you will make requests to. So we talked about, or you must have talked about, the client server architecture, where clients make requests and servers have data. Well, in this instance, our web servers are going to be both client and server, depending on which end of the communication they're on. They are the server for the front end, but they're the client for the RDBMS. Okay? Cool. All right, so there's our RDBMSs. Let's see how we're doing. Introduction to RDBMSs, the relational data model, tables, columns, and rows, and select statements. So why don't we jump right into so-called select statements. Feel free to jump right in and interrupt me. The first half hour or so is going to be just like this, theory, and then we're going to jump right into a series of select challenges that I have for today, where we're actually going to query a database, and we're going to look at how that actually works. Cool. Okay, so select is the most basic of the SQL statements. Okay, a select is it's the R in CRUD, or if you've heard of bread, it's the BR in bread. Okay, so today we're going to learn how to read data. Cool. So it has the simplest syntax as well. Is everyone ready for the hello world of SQL? Okay. Select star from table, semicolon. That's it. This is the equivalent of console log hello world when you're learning how to JavaScript program. Okay. If we break this down, select tells us these are the particular fields that we want. So if we were querying from this table, country, salesperson, order date, we would have to make reference to the particular field. Asterisk is a wildcard. You've probably seen that in a bunch of different places. Like, let's say if you're trying to ESLint more than one file at a time. You can also specify, what did we have here? Country and salesperson, I feel, would be slightly different than salesperson. But you might be more likely to want to see an salesperson at some point in your day. Thank you for the week 9 laughter over there. Select country and salesperson. Okay, so we can select specific fields, and then we say, obviously, what table are we interested in? Because any database is going to be, as we said, a collection of tables, right? So we have to specify from the database, look inside this particular table and give me back all the records and these particular fields for those records. Okay? So we'll usually, oh, very nice VS Code. Okay. So for the rest of today, for the most part, I'm going to deal with select asterisk. Okay? Which means just give me back all of the fields, just everything. Because for clarity, I think that's a little more reasonable. You'll probably talk tomorrow. I'm not giving you the lecture tomorrow, but you'll probably talk about why selecting star is not a good idea. And if they don't bring it up, ask them why selecting star is not a good idea. Cool. But for today, we're going to do it, but just know that it's for clarity purposes. I want you to focus on the rest of how select works and not so much on what particular fields we're getting back. Cool? Awesome. Okay, so why don't we jump right into our first select challenges. So for the first 5 queries, we're going to be using the users table. And for your notes, you'll actually be able to see that image. But I have a better one here. Okay. So here we have, this is what's known as an ERD. You'll get more into this tomorrow, an entity relationship diagram. So this is our users table. Last night, while I was bored, I generated 10,000 random users. So we're going to run some queries against this particular table. But it's important, as I said, everything conforms to the same structure. So we need to know what the structure of our table is in order to be able to query against it. So here's our users. They have a primary key of ID, and we'll get more into why we're using primary keys in a little bit. Just accept that we have a primary key there. Then each one has a first name, a last name, an email, an age, a country of residence, and a payment due date. Because as Nima will point out, what are we interested in? Exactly, money. Users paying to use our application pays our wages, right? So ultimately, this is what we're concerned about. So for today, money. We're going to be concerned about when this payment due date comes up. Awesome. So there's the structure of our data. Cool. So I'm not actually going to use PSQL. Give me that back. Although it's a great system, I like to use an online GUI to interact with my databases. Okay. So jump back here. So Elephant SQL is an online resource that does exactly what it says. The reason why it's an elephant is because the symbol for Postgres is an elephant, because an elephant never forgets. Thank you. Awesome. That's how I should phrase all my questions, is just leave a blank there. Cool. So it's Elephant SQL. All of these are Postgres databases. They live in the cloud. I find it really handy for myself professionally, as well as when I develop my own applications, to have my RDBMS completely external to my app, not running on my machine. So here we can see, I'm not going to expand this because it actually contains the password, but remember what I pointed out. The URL to this database, if we want to connect remotely, starts with Postgres, right? Remember when I said that we'd be communicating over the Postgres protocol? So instead of seeing HTTP here, we're seeing Postgres. If we were doing MySQL or SQL Server or something, they'd have their own custom protocol that we would connect over. Cool. Okay, so we're going to jump into the browser. And we know that we have a users table. So I am going to select star from users. Always remember semicolon, especially when you're in PSQL. This will happen all the time, that you'll enter a query and then you'll press enter and nothing will happen. And then you put a semicolon in and press enter, and then it runs. Okay? Semicolons tell SQL, we're done. This is a complete thought. This is the end of the request I'm making to you. And then we execute. And the beach ball is going to spin for a while. And we can see that we have 10,000 completely randomly generated users. So that's why if you see that Dora Burge's email is nina16@hotmail.com. So they don't match up at all. We can see that we have some younger users here. Look at this, 4 years old, already has an email address. Kids nowadays, I was like 15 before I got my first email address. Also, making their payment tomorrow, I hope. Otherwise, we're going to have to send somebody to find this 4-year-old in Bhutan. All right. So there we go. Oh, look, we got a 0-year-old. Fantastic. See, everybody's remembering 4 weeks ago when I gave this lecture. Awesome. Okay, so let's take a look at the first of our select challenges. List the total number of users. Well, I already told you that I generated 10,000 users. Presumably, you can see how small the scroll bar is. If we scrolled all the way down, then these IDs would go all the way to 10,000. But that's not very practical, right? So there must be some way for us to tell SQL, oh, by the way, we are going to be practicing declarative programming today, as opposed to imperative. So can anybody tell me what imperative programming is versus declarative? Imperative is what you've been doing so far. All of your JavaScript has been imperative programming. You explicitly tell the computer what to do. You say, I've got an array. I want to iterate over this array with a C-style for loop or with a for each. I want to look at each value and I want to double it, or I want to console log each value or something like that. But you were explicitly saying, iterate over this, give me back each value, perform some operation on this value. Okay, I'm done with this. Moving on to the next line of code, right? So that's imperative. In declarative, you ask the computer to please do something for you. You say, could I select all of the records from this table? We don't explicitly say, I want to iterate over each one and I want to console log it or I want to perform some operation. We tell the SQL engine, please do this thing for me. And it will do it for you. We don't get into the nuts and bolts of the how. We don't care how it's implemented. Remember, we talked about abstraction layers. And this is what we do as programmers. We interact with interfaces that have abstracted away all that complications for us, right? So we can just say simple things like select star from users, and we get back every single user in the database. I would challenge you to write a line of JavaScript code that does something similar without having to, Okay, so because it's declarative, presumably there's going to be a super simple way to return how many records are in this table. How many users do we have in our database? And we do. We have a couple of already created SQL functions for us. And one of them is count. These are what are known as aggregation functions. They will aggregate our data together. They will collapse it into usually a singular value. So if you're familiar with like array.reduce, how it can take an entire array and collapse it into a single value. Remember I said I was going to be referencing array a bunch. So count does the same thing. Instead of giving us 10,000 records, it gives us one record. It collapsed all of our data down and said, okay, I've ran that for you. Select count, gives you back 10,000. So whatever you put inside of here is what it would count. So if we go back to selecting star from our users, let's say this information wasn't complete. Let's say we had a bunch of users that were missing ages, let's say. So if we did select count age, then we would get a different number. Why are you? There we go. Elephant SQL has these weird things where occasionally the query doesn't run correctly, and you have to hit execute. But I usually rant and rave about Elephant SQL so much that previous cohorts have asked if I have some kind of like affiliate code that you can use to save on like a premium membership or something. So in light of that, don't forget to like and subscribe. Smash that notification icon so you're notified whenever I go live, and use the affiliate link in the description down below. Awesome. Cool. So we can pass in any field that we want into count. Typically, you'll do count star. You'll say, I want the number of all of the records that came back. But occasionally, you'll want to plug in something like ID or something like that, like just to give you a count of whatever's in there. And as we've seen, we get back 10,000. Fantastic. Challenge 1, complete. List the total number of users. List users over the age of 18. There we go. So this is going to introduce us to the where clause. So we refer to all of these as clauses. If we define clause here, not to be confused with Santa. I like the second one, a particular and separate article, stipulation, or proviso in a treaty, bill, or contract. So we actually can write our SQL with various different clauses. And if you're interested, we'll go over this later. But here are all of the clauses that are available to us inside of a select statement. And this is the order. I will share this link and we'll review this again later. But this is actually the order that you would state them in. Select, from, join, on, where, group by, having, order by, limit. Okay? So we are interested in the where. Cool. So if you're familiar, again, with, there's an array method that only returns certain results that pass a test. What method is that? Filter. Exactly, array.filter. And what do you pass to filter? You pass it a callback function that would then test every element and says true or false. Does this pass this test? Are the users over 18? Is this particular user logged in? Do they have a short URL? Things like that. And you filter down from all of your array values down to a few, whatever passes that test, right? So we can do the exact same thing here. We just add a whole new clause. Oh, and I should point out before we move on, SQL is completely case insensitive. It doesn't care whether it's lowercase, uppercase. The convention that I've been using to capitalize everything makes it a ton easier to read what's going on, because you know that all of your, actually this will be uppercase because this is a built-in function. You can tell because your lowercase things are what you're in control of. Those will be your table names, your field names, your limiters, things like that. So when you're scanning through the SQL, you can say, okay, capital, that's keyword, keyword. Okay, lowercase, that's something I can interact with. That's something I can change. And when we start writing more and more complex things, you'll see why it's advantageous to have these as capitals. The other thing that I've been doing is putting each thing on a separate line, which also makes it easier. Like imagine that we were saying select ID and first name and age, something like that from users. This, having them on separate lines, makes it a lot easier to go in here and say, okay, give me another field, right? Rather than having them all on one long string, okay? But bottom line, SQL doesn't care. It's just looking for this semicolon to say, yeah, I'm done with my thought. You can do it all on one line. You can do it on 15 lines. It doesn't care. This is purely for readability, okay? So, back to where we were. List all of the users over the age of 18. Cool. So we want to start off by selecting asterisk, select star from users. And then we're going to introduce the where clause. And where is just like filter. It will look at this and it will evaluate whether this is true or false. So we say where age is greater than 18, all the users over the age of 18. Is this true? Keep that record. If it's false, throw that record away. We're not interested in it. So when I execute this one, we'll see that all of our users are now over the age of 18. You won't find any 0-year-olds that fell through into our data set here. But we'll also see, hopefully, that we're missing some IDs here, right? This is clearly less than we had before. And we can find out just how many less by throwing in our count. We have 5,400 users over the age of 18 in our database, which makes sense because I had our users randomly generate between 0 and 40 years old. Okay? So this is kind of interesting then, because what is this? This looks an awful lot like a table, doesn't it? But it's clearly no longer our users table. Right? Because our users table has 10,000 records. We just counted it. This record set only has 5,400 records in it. Right? We're missing 4,600 records. So this is another thing that select does for us, is it actually creates a temporary table. It creates a temporary table. This select statement creates a temporary table in memory that matches the conditions that we specified. So this is actually a temporary table that goes away as soon as we try and run another query. It only exists for the lifespan of this query. And then beyond that, only if we were to store it in something, otherwise it just gets thrown away. Okay? So there's our where. We can add conditions into here. If we wanted to say, I want to see everyone younger than 18. Cool, easy. Less than or equal, as you probably guessed, greater than or equal. Anything that you can do in a JavaScript conditional, you can do in here, okay? You could say, you could have something match specifically, where first name equals Florian. Our first error of the day. You're going to see a lot of errors today. And what is programming? It's dealing with errors, right? Column Florian does not exist. And this could be a super cryptic one if you don't understand what SQL is actually trying to tell you. It is presuming that this is a column name. And the reason why is because column names in SQL are always surrounded with double quotes. It doesn't perceive this as a string. It perceives this as this is a literal column in this table. So it's saying that column Florian does not exist. So if you want to pass a string, you've got to use single quotes, okay? And then let's see how many users. 4 of our random users have the first name of Florian. What a great first name. That's fantastic. Does anyone have kids? Have they gone through the hardship of trying to name their children? Nobody? Not yet? Okay. It's a big deal. It's one of the hardest things you can ever do in life is give another human a name that they're going to be saddled with for the rest of their lives. Okay. But Florian, excellent choice. I fully approve. Anyone who wants to name their child Florian. Okay, cool. So here we're saying, does it equal? Yes. So this is exactly what our where does, is it filters down our results and gives us back only those that this resolves to true for, okay? Just like array.filter. Cool. Don't do that. Has anyone ever found a time when this has been a useful thing to do? I've never done it purposefully. Anyway, okay, cool. There we go, moving on. 2 out of 11, and it's only 10:37. Please feel free to jump in if you have any questions at all. Okay, question number 3. List users who are over the age of 18 and have the last name Barrows. Cool. So this is going to be another single table query. Where with and. Cool. Okay, so let's build upon this. We want to select star, as in give us back all of the fields from users where age is greater than 18. And now we need to specify a secondary condition. And the way that we do that is with the keyword and. There's also a keyword or, if you're interested. You might be familiar with ampersand ampersand or pipe pipe. It's the exact same thing, except we're explicitly saying and. And you'll notice that a lot with SQL. It's written like English because it's a declarative language. We're saying where this condition and a new condition. So we said last name equals Barrows. So it will look at this and it will say they have to be over 18 and the last name has to equal Barrows. Run that. Hey, look at that. Significantly less, but we were able to succeed. Okay. So you can actually chain on. You could have ors. You can have multiple ands. You can chain them all together just the exact same way that you would use ampersand ampersand in JavaScript. Cool. That's literally all there is to that. We're just extending out the filter. Okay. Cool. We are moving at a brisk pace here. List users over the age of 18 who live in Canada, sorted by age from oldest to youngest, and then last name alphabetically. Who writes these things? I don't know. Okay, so just like the rest of our programming, we're going to use an iterative approach, okay? We build things up. I doubt there's very many people who can write a multi-line SQL query start to finish without error. You'll always want to build things up and check out the example data that's coming back and say, is there anything still in this record set that I don't want? Is this doing what I actually want it to do? So when I'm developing, I will play around inside of this GUI till my SQL is perfect. Then I'll cut it and paste it into my JavaScript. Okay? So, step 1. List all the users over the age of 18. Okay? We already know how to do that, where age is greater than 18, who live in Canada. Okay, so how are we going to specify users who live in Canada? And country equals Canada. Awesome. Let's see how we're doing. Perfect. We don't see anyone under the age of 18, and all of the country say Canada. Awesome. Next, sorted by age from oldest to youngest. Ooh, we're going to introduce you to a new clause. And that clause is order by. So there's an array method called sort. Has anyone ever had to sort their arrays before? And what does sort do? You pass it a callback function. It compares one value to another value, and then it sorts them. You could say, is this value greater than this one? Okay, reverse them because I want it from lowest to highest, or vice versa. And you can actually get into very complex sorts with arrays of objects. You can compare specific properties against other properties and arrange them however you want. Okay, so this is what order by is doing. This gives us back 100% of the records, right? This filters that down to just a subset of those records. Order by tells us how do you want these records ordered. Okay, so we said order by, sorted by age from oldest to youngest. So let's just throw in order by age and see what happens. Ooh, 19, 20, 21, 22, 24, all the way up to 39. Okay, so we learned something. That the default sort order is ascending. Okay, so if we do this, we see that that's the exact same thing. You can pass in a second argument to order by. You say, I want to order by this field, and either ascending or descending order. And as we just saw, you don't have to specify ascending because it's the default. Okay, but we said sorted by age from oldest to youngest. So we actually have to pass another argument, descending. Cool. Let's execute that. There we go. Now 39's on top, all the way down to 19. Great. And last name alphabetically. Okay. So we were able to add another condition to our where by throwing in the and keyword, right? So presumably, naively, I would try and. And we said by last name. Last name, ascending. Syntax error, at or near and. And it will actually point to the thing that's giving it the trouble. So it's saying, what are you doing here? I don't understand what you're doing. Any other thoughts on how we could specify another order by to our query here? How are we going to get it to listen to this last name? Let's try that. Let's move to another order by. Syntax error at or near order. It doesn't seem to like that we are adding another order by clause. It seems to have a limit of one order by clause per query. That's fair. Maybe? Awesome. There we go. So we have actually filtered this twice, and hopefully I'll be able to demonstrate that from our record set. The first option is age descending. So we can clearly see that it's ordered by age descending. But then we said last name ascending. But if we see H is before O is before J, did our last name sort actually take? It did actually. So if we look at somewhere where age is tied. So what this says is sort by age. Great. It doesn't care about any of the rest of the columns. It just looks at the age column and then sorts by that. But then we specified a secondary sort. When these match, when your ages match, then sort by another value. So if we look at these two 35-year-olds here, it actually sorted them alphabetically by last name. Do we have any other duplicates? There we go. K comes before S, right? Here, we've got 3. So HAA comes before HAM, comes before K, okay? So you can actually chain these along, and you can have more and more depending on how you want to order your data. And this clause is extremely important because there is no guarantee about how your records are going to come back from the database. When we said select star from users, we got back everything with that ID, right? It was because this is the way that I created it. It shows up and it says 1, 2, 3, 4, and the beach balls spin for a while because there's 10,000 of them, right? But I would never, ever bet my application performance any kind of money on the fact that this says 1, 2, 3, 4, 5, 6, all the way to 10,000. Because there's absolutely no guarantee that that is the case. There's nothing in SQL that says, give it back in creation order. Give it back in any order at all. If we ran this a million times, sometime we might get 1, 2, 4, 3, 5, 6. Okay? And to the database, it doesn't care. You said, give me back all the records. I gave you all the records. What more do you want? If you want to, oh, this is another great thing about Elephant SQL, right? Use that promo code. It stores your previous queries, so you can just jump back to them. Okay. If you want your data in a particular order, if it's important that it comes back in a very particular order, order by. That's the only way to guarantee that it will come back in any conceivable order, okay? So if you need it to be ordered, order it here. And if you're wondering, well, you're going to show us on Wednesday, Andy, or someone's going to show us on Wednesday, that I can do this with JavaScript. Why wouldn't I just select star from users, get back that array of 10,000, and then manipulate it with JavaScript? I know what I'm doing with JavaScript. Why do I need to learn more SQL? And the answer is SQL is incredibly optimized. It was invented in the late 70s and perfected. That there's been no or very little iteration on it other than different data types since the 70s. It was a perfect system when it was created. Okay? So it is incredibly optimized and incredibly fast. Way, way, way faster than JavaScript. Carl Jensen, the lecturer, ran some benchmarks against it, and it was somewhere in the region of 100 times as fast to write a better query than it was to do the manipulation in JavaScript with a worse query. Okay? So if you're concerned about speed, write a better query. Okay? Awesome. So is that clear? This is how we order our records. If you want a specific order, this is it. Okay? Cool. So we turned our word puzzle of list users over the age of 18 who live in Canada, sorted by age from oldest to youngest, and then last name alphabetically. I feel like there should be a comma in there so that I can take a breath. Okay. And that's exactly what we did. We said, give us back all of the records from users where age is over 18, country equals Canada, and then order them by age descending and last name ascending. And as we saw, ascending is the default, so you don't even need to specify that. Okay? Because what are programmers? Lazy. Exactly. And what's the laziest thing you can do? Use the default. Okay? So we love our defaults as programmers. Cool. This is our last single table query, and then we can go for coffee. List users who live in Canada and whose accounts are overdue. See, here's where that 0-year-old is going to get into trouble. Okay, so where country equals Canada. So we've got our users, and we want to find out whose payment due date is in the past. Who hasn't yet made their payment for the month of November? Because we're the 11th right now. So here we go. Jamar Cronin is behind on their payments. So we need to find out. Accounting just emailed us and said, give us back all of the users who live in Canada whose accounts are overdue because we're going to send everything to collections, right? And then they're going to get phone calls and stuff like that, right? This is what we do as programmers, right? We are responsible for all of those phone calls that you get at 2 a.m. that says your account is overdue, okay? Awesome. So we know we're going to need some kind of and, right? Because we're filtering again. We're not interested in Danica Farrell here because that account's not yet due. Okay, cool. So we know that we need to specify payment due date somehow, and it's going to be less than something, right? So what if we said, okay, this looks like it's year, month, day. What if we throw in year, month, and day? Less than today, right? Sounds fair? Ooh. And now you can see that all of our payment due dates are less than 11/11. So all of these people, including this Mackenzie Schoen, is going to get a phone call, right? So what can you do? Good enough to get an email address at 0 years old, but not enough to pay all their bills on time. There's a certain level of maturity. I feel like their 7 and 8-year-old customers probably pay their bills on time. Okay. Awesome. So this actually works. But this would be a pretty terrible query, right? Because what do we do next month? We'd have to rewrite it, right? We'd have to go back in. Maybe we're going to parameterize this with JavaScript, and we're going to throw this in as a dynamic variable or something. But we're still going to have to go back and change that variable every month. And what happens if this is just one of 1,000 queries that we're running, that we're responsible for? Then we got to go back in here every single month and update them all, change the variables, look at all these things, right? Wouldn't it be great if there was another built-in function? And there is. And that function is now. Now gives you back the current date and time. So in other words, literally right now. So here we can say, and payment due date is less than now. So if we run this again, we'll see that we got the exact same results. But this is now, we can run this any day of the month. If it's the 24th, we can run it again and see who's behind on their payment. If it's the 25th, all we have to do is say, run that query that I wrote yesterday, and that's going to work until the end of time, because it's always going to be now. Cool? There's a ton of these built-in functions, like on the order of hundreds. If you want to do something, just Google it, and you'll get like a Stack Overflow, or you can look at the Postgres docs. In fact, why don't we look at the Postgres docs for now? Ooh, postgresql.org. Date and time functions. All right. So let's see if we can find now. Hey, there's the now function. Timestamp with time zone. Current date and time. And if you're wondering about timestamp with time zone, timestamp is a particular data type. You'll talk about them tomorrow. But this particular one adds on the time zone. So it's the time zone of the server. So if your server's running UTC time, then it's going to come back as the UTC. So keep that in mind when you're calling your customers to harass them, because their payment might not be overdue in their time zone, but it's overdue in your time zone. Okay? So just keep that in mind. And it returns the current date and time. We can see that we have a ton of these. Local time, local timestamp, justify interval, is finite. Sure, that sounds great. Date part, current timestamp, current time, current date. So time of the day, things like that. So if you're interested in how do I retrieve a particular thing, just look at the docs. They're pretty good for Postgres. Cool. So here we're saying select all of our records from users where country equals Canada and payment due date is less than now. Awesome. We are finished the first 5 of 11, and it is 10:54. Why don't we take a coffee break, and then we'll get back to 2 table queries. All right, thanks. We'll be right back. All right. Everybody's back, looks like. Everybody ready to be bored for another hour? Yeah. It's great. Fantastic. Yes, awesome. This is great. Okay. So, for the first half of the lecture, we talked a bit about RDBMSs and databases. And then we did some simple select statements against a single table. One, a single table database is not incredibly useful, right? We haven't really gone beyond like an Excel file. So we're not using the power of relational databases. And two, most of your select statements that you'll write as a professional will be multi-table. Because again, for that very reason, a single table query just doesn't give us back all of the data that we want necessarily. Okay, so we're going to move into multi-tables and the other portion of relational databases. But first, if we're going to have one table relate to another table, so in other words, the record in this table relates specifically to the record in that table, we're going to need some way to identify particular records. Particular records. Okay, so let's move outside of the world of databases for right now. Let's move back to something that we can all kind of wrap our heads around. We have a cohort. Let's just say we have a cohort full of students. I know it's a little out there, but if you can follow along. Okay. Someone hits request for assistance. Again, I know it's out there, but how does a mentor know who to go to? How's the mentor know where to go? How do we know who hit request for assistance? Yes, but that user, like if someone comes in and they just ordered from Foodora or something or DoorDash and they say, delivery for Andy. Wait. That was a little too on the nose. They've got a delivery and they come in, but there's 50 people here. It's not as evident as when they come to my house and they're like, hello. And I'm like, yeah, I'll just take that. I'm the only one here, right? They show up, some poor DoorDash person comes in and they're like, I've got food. How do they identify who the food is for? It's going to have a name attached to it, right? Because presumably our names are unique enough to identify us, right? But that might not work. You say this is for Andy, and we have Andrew is a very common name. We might have multiple people in here named Andy. So then it's like, Andy who? Right? We need more information. Then they'd throw in like a last name or something like that to identify a particular person to make sure that that food gets to a particular individual, right? Presumably whoever ordered it, but you never know. Maybe they're not here and you're just going to eat their lunch. But we need a way to identify, in particular, a record in order to be able to relate some other records to that one in particular. We need some way of uniquely identifying a record. And we have a way of doing this in... Yes, thank you. You jumped right ahead. We use primary keys to identify records. And they will usually be sequential integers. There we go. Integers. And this is preferable. Again, you're going to talk about this tomorrow. And hopefully you can press the lecturer on why integers are better than strings or something else like that. Why did I not just use first name as my unique identifier for all the records here? And we've already kind of discovered that if I said that first name, semicolon, execute, that wasn't unique enough, right? Just like when Foodora shows up, first name was not unique enough, right? But if I said something like where the ID equals 551, I get back a single record because it uniquely identified that particular record, right? That particular row, we said, has an identifier of 551, right? And we can do that for any one of them. I don't know what 5,551 is going to be, but Julian Bosco, apparently. There we go. With Vilma Karachik at gmail.com. Age 26, lives in Martinique. Awesome. Payment overdue. That was a good one to randomly. I'm going to send this one to accounting. Okay. So we need some way to identify our records. We use primary keys. And we just, every single record gets this primary key. We specify that the table has an ID field, a primary key, and that every single record is going to be identified in this way. Okay? So if every table has a primary key, we need a way for another table to reference this field. We need a way for another table to reference this record. And obviously they'll point to the primary key, but it won't be the primary key in that table because that table is going to have its own primary key. So what do we call a primary key that we store in another table? What do we call a primary key from one table that we store in another table? Foreign key. Thank you. Foreign key. There we go. A primary key stored in another table. And it doesn't just point to this column here. If we had users and we had user ID of 5551 and it was associated with, say, a blog post, and we said this user, or a shortened URL, if you will, maybe to bring it a little closer to home, we say this user is associated with that particular blog post. But it's not just pointing to this 5551. It's pointing to this entire record. So if we say that blog post points to this user ID, we mean this entire record, not just the ID. It's just we don't need anything more than the ID to identify someone, right? We don't need anything more than this unique identifier to identify who it is that belongs to that blog post or that shortened URL, okay? So foreign keys, and again, you'll talk about this more tomorrow, take the form of usually table underscore, so the singular of the table underscore ID. So if we're storing the user ID in another table, that this is the users table, but we're referencing a particular user. So we'd say user underscore ID, and that's how we'd store it. So anyone else reading your code says, this points to the users table. And if you had like a blog post ID, you might have blog ID, right? Or you might have post ID, or you might have email ID, or something like that. But you know that you're going to be looking in the posts table. Cool. Primary key, foreign key. So there we go. We also need to look at types of joins. And these should not be confused with relationship types. That's not the same thing. You'll hear tomorrow about one-to-one, one-to-many, many-to-many, stuff like that. That's all for tomorrow. Don't get the type of join confused with the type of relationship that two tables have. Okay? This is a different thing. Joins are just about how we're going to take two tables or more and mash them together to get a result set. Okay? Because let's move on to, before we get too much into joins, our next 6 select challenges are going to be using the albums and songs tables. So we're going to skip over to albums and songs. So here we can see that our albums table has a primary key of ID, nice and simple, then the album name, artist name, and release date for the album. It's joined to the songs table, which has a primary key of ID, nice and simple, a foreign key of album underscore ID, which points back to the album, then the track number, as in where it is on the track, on the CD, if you're still buying CDs, song name, and an arbitrary rating that I gave each one. I didn't get these ratings from Spotify. I actually just added my own random numbers. Cool. So we can see that this line, and you'll go more into this tomorrow. Yes. Hi. So for Calgary, the question was, the first part of the foreign key should be the other table's name. Yes. And why is it album? Hopefully I mentioned, I'm not sure if I did, but you use the singular, right? So where did I write that? Like user ID or post ID, because you're referring to one particular record. You're not referring to the albums table. So albums is a collection. Just like it's good practice to always name your arrays plural. It should be like users, shortened URLs, stuff like that, because it's a collection of things. So this is the albums table with a whole bunch of singular albums inside of it, but we're not making reference to that entire table. We're making reference to one particular album. Okay. So, wow, there we go. So the way that this is going to work, and we'll check out the data in a second, is that each song is going to be associated with an album. Okay. And so all of the songs will live in the songs table. All of the albums information will live in the albums table. But we need to put these together because individually they don't make a ton of sense. So let's jump back into Elephant SQL just so that we can look at the albums database. Okay, so first off, let's take a look at select star from albums. Execute. All right. So what I did was I looked at like the Canadian top 40 and just grabbed some random ones because oftentimes I have trouble, because I'm so old, coming up with analogies that students understand and things that they can be interested in, not yawn all the time. So some of these artists I know, some of them I have no idea who they are. Like Beyonce is... Oh, is it Beyonce? Oh! Okay. Beyonce, that makes more sense now. Okay, so not Beyonce is what you're saying. Okay, awesome. So, see? Youth. This is how I'm identifying. I'm cool. Okay. It's cool people tell you that they're cool, right? That's how it works? Yeah. Okay, awesome. So this is what our albums look like. Obviously, each one has a primary key. Then we've got the album name, the artist name, and the release date of the album. And if we jump over to songs, we can see that we have a whole bunch of songs. Each one has a primary key, as we saw from our here. Where are we? Elephant SQL. The album ID, the ID of the album that it belongs to, the sequence of where it belongs on the tracks, like the track number, the name of the song, and some arbitrary rating that I assign to it, between 1 and 5. Cool. But like I said, if we just select star from songs, this doesn't really help us because which album contains the song Lift Every Voice and Sing? Unclear. Which one has I Been On it? Who knows? The database knows because of the relationship between the two tables. We've said we're going to store the foreign key in the songs table, which makes reference to that entire record in the albums table. Cool. So, and hopefully you'll talk more about this tomorrow, but the idea of a database table, how it differs from, do I still have that, from like an Excel spreadsheet, is that it's not supposed to be human readable. Okay? The queries, the querying language, stuff like that, is all supposed to be human readable. The contents of the table is not meant to be read by a human. Okay? And we can see that here because what does album 1 mean to anyone? Does it mean anything to anyone? What did user 5551 mean to anyone? It doesn't mean anything. If you're looking at a table, it's going to be a whole bunch of integers that may or may not be human readable. They may or may not mean anything to you. We give it meaning by pulling it back apart again, pushing it together again, by saying, give me back the album that matches this query and associate this song with it. Okay? So that's what we're going to be doing right now. So we have various different types of joins. And I actually have a visualizer here. Oh, awesome. Cool. So let's clear that. So is everyone familiar with, and I'll send you the link to this so you can play with it later. Is everyone familiar with Venn diagrams? Okay. So let's say that we have two tables that we wish to join. Let's say A is albums and B is songs. Okay. So let's start with the most basic join, the so-called inner join. And this is the one that you're usually interested in. This means I've got this entire table of collection of entities over here. I've got this collection of entities over here. Give me back where they are the same, where they match up. So in other words, where each song has an album associated with it. Don't give me back any of the songs that aren't associated with albums. Don't give me back any of the albums that aren't associated with songs. Give me back where they match up. So this is the most common type of join, the inner join. And in fact, since it is the most common type, it's the default. So we don't actually have to type inner anywhere. We can actually just type join, and SQL says, oh, you must mean inner join because you didn't specify another type of join. Okay, so we can take advantage of those defaults. So we've got the inner join. Beyond that, we have a left join and conversely a right join, depending on which side of the relationship you're on, depending on how you wrote your SQL. Left will refer to the first table that you mentioned, and right will refer to the second table that you mentioned. Okay, so this says, give me back all of the records from table A, including the matching records from table B, but don't give me back any of the non-matched records from B. And same thing from the B side. Okay? Ooh, B side. And we're doing albums and songs. Oh, this is just, I should be a stand-up comedian, I think. Okay. So these are helpful to us because we might say, like, give us back all of our users, regardless of whether they've made blog posts or not, regardless of whether they've shortened any URLs. I want to see all of the users. And in order to do that, and we'll do this later, you need to have a left join. This is saying, give me back everything from here, including where they're matched up, but nothing from B. Okay? So these are our left and right joins. So we've covered inner joins, left and right joins. Now, what happens if we remove this and we just say, give me back from A? This is what's known as an outer join. If this is an inner join, where they share data, this is an outer join. What this says is, give me back all of the records from table A, but not any of the ones that are matched to table B, and nothing from table B. I'm not interested in those. Outer joins are less common because this isn't usually something that you're interested in. Usually we're interested in the relationship between tables, right? So this would say, give us back everything from here. So if we had albums that don't have any songs associated with them, it would give it back to us. Why you would use this in the real world is you might be interested in which users signed up for your service, but they haven't yet shortened a URL. They haven't yet made a trade on your platform. They haven't yet posted a blog post. So this is where you can send them a follow-up email and say, hey, you registered a week ago, but you haven't actually done anything yet. So a left outer join would give us back that data. And conversely, a right outer join would show us where blog posts are not associated with any users. In this instance, it would be called an orphaned record. A child record that has no parent record to relate to is called an orphaned record. So we have two options for this. We have our left outer join, we have our right outer join, and then we have what's known as the full outer join. I have never, ever used a full outer join in practice. It's only when I'm doing like some kind of like learn SQL tutorial that I'll do a full outer join. Because this would say, give me back all of the albums that don't have songs and all of the songs that don't have albums. Maybe you'll need to use it one day. It's important to know about it, I guess. So we have our inner join. We have the left and right joins that complement that. Then we have a left outer join, right outer join, and full outer join. So we have 6 join types that we'll be interested in. Primarily today, we're going to deal with the inner joins. Like, how are these two tables related to each other? Okay? So let's see that in action. Let's scroll all the way down to question 6. List all albums along with their songs. And here we have to take advantage of an inner join. Okay? So we'll jump into here. So we want to select star from albums. Okay? That's a good place to start. Like I said, I want to work iteratively through this. It's not a process where you just throw all the SQL at the screen and hope for the best. You want to build these things up. Okay. So this gives us back our single table. And now we need to join. We can actually inner join. And we're going to inner join with songs. Okay? How? And on is how we specify how the two tables are joined together. Because SQL, even if our database knows that there is a relationship between these two tables, and this is how they're joined together, it's not smart enough, or they didn't make the design decision to say, I know how these are related together, so I'm just going to do a simple query and give them back. We have to explicitly say, how are these two tables joined together? Okay, so this is where on comes in. So we have to make reference to some field from albums. So it's going to be the album ID, right? The primary key, equals, and what did we call the foreign key? Album underscore ID. So we're saying, join these two tables together, select star from albums, inner join songs on albums.id equals songs.album underscore ID. So if it has an ID of 1, then where we saw that in our songs, where there's an album ID of 1, plug this record into that place. Okay? So let's run this and see what happens. Hey, that's a little better. Now we see that we have Homecoming by Beyonce. Is that? Yeah. Okay. We see the release date. We see the album ID because we said select star. We weren't particular about what we get back. We said give us back everything. Then we get the track number, the song name, and some arbitrary rating. And this is, you could argue, this is a lot more human readable and getting closer to this thing, right? So this is the purpose of our selects, is to put the information back together again into something that we can use as devs, something that makes sense. Because now we could take this and we could render it on a web page, right? In theory, on Wednesday, you'll see how to marry these two things together. But now this makes sense. We have the album name, the artist name, and then all of the songs that are on that particular album. And then it switches over to Jenny Lewis's album, and then Ariana Grande, and then Post Malone. Oh, okay, so for Calgary, the question is, does the order of these two things matter? And let's find out. Equals albums.id, execute, doesn't matter at all. So that's absolutely the short answer. It's an equality. It's saying this matches that. So whichever one doesn't matter. I prefer to do, just to keep it straight in my head, the first table. So in other words, the left one, put its information on the left-hand side of the equation. The other table that we're joining with, put that stuff on the right-hand side. That's just an arbitrary decision that I made. You can specify these in any order that you want. Okay? But we've told our engine to match these together on that field. And this is the most common thing that you will do, is you'll match up based on the foreign key and the primary key, because that's how your data is actually related. But you don't need to do that. And that's why it's not the default. That's why it doesn't implicitly give you this table matches that table. Cool, here's all your records again. Because if you recall, from our users table, we had primary keys from 1 to 10,000. So I could, and this might be a little bit out there, but I could join up the users table on the song's ID and say user ID equals song ID. And then I'd get back whichever user is associated now with welcome, whichever one had a 1 in it, right? I wouldn't want to do that, but if you need to, that's where comes in handy, okay? So this is the simplest of the joins. This is how we would just do an inner join, and I just want to demo it for you. Once again, inner join is the default, so you don't need to specify inner. So we were able to list all albums along with their songs. Cool. List all albums along with how many songs are on each album. So we're going to introduce a new clause here, but we'll get to that in a second. Okay. So right now we're seeing all of the songs. We're just seeing 100% of it. Okay. So we know that we're going to have to join these two together somehow, but we're also going to have to aggregate this somehow. So let's go up here and we'll say that we want albums.album name. By the way, you also don't need to do this. This is me being explicit here. I'm saying from the albums table, give me back album name. You could actually do without that. I prefer to be explicit, because what if you had two tables where there was a name in them? The SQL engine's going to throw an error because it's going to say, I don't know which name you want, right? So it's a good practice just to be explicit about your table names. So here we want albums.album name. Let's see what happens. Okay, cool. So far so good. We're seeing a whole bunch of these, but we want to actually squash these down. We don't want to see homecoming, 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 homecoming. We want to see one line for homecoming and then how many times that appears in the songs table, right? We want to see one entry for on the line and then how many times that appears, right? So we're going to need, how did we decide that we were going to count our records? Count. Exactly. So what do we want to count? Because we don't just want to count star. We want to count something in particular. So how would we get that? By the song's ID, right? So we're going to say, let's count the song's ID and let SQL take care of the rest. Cool. Execute. Again, this is another error that you're going to see throughout today. So I'm saving you a mentor request for assistance. SQL is saying that column albums.album name must appear in the group by clause or be used in some kind of aggregate function. So what this is telling us is this is an aggregate function. This is taking a whole bunch of records and squashing them down to a singular value. But as we saw from albums.album name, we saw homecoming, 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 homecoming. We're not doing any kind of crushing or aggregating on the album name. So it's telling us that it must appear in some kind of group by clause or be used in an aggregate function. We're not wrapping it in a count or a min or a max or an average. So let's do what it suggests. Add our new group by clause and throw in album name. Ta-da! There's multiple points for applause. And yes, thank you. So we did exactly what that error told us to do. We said throw it into a group by clause. So what group by is used for is it's an aggregate function for when you don't have an aggregate function. What it will do is it will look at all common records. So we saw homecoming, 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 homecoming a whole bunch of times. We're saying group all of those instances together. Crush them all down into one thing. So you can think of group by as an aggregate function, but we're not counting, we're not getting the minimum or the average. We are just crushing them all down to a singular value. So it took every single instance of Hollywood's Bleeding and crushed them all down into a singular instance, and then gave us back the count, the number of times that record appeared in the other table. So we can see that On the Line has 11 songs, Homecoming has 11 songs, and Thank You Next has 9 songs. Cool. Any questions about group by? Because that is usually something that students have trouble wrapping their heads around. Anything? All good so far? Cool. All right, let's move on. You are going to write so many queries today. It's unreal. You're going to get intimately familiar with all of these different clauses. Okay. Number 8, enhance the previous query to only include albums that have more than 10 songs. Great. So, this is an opportunity to talk about aliases as well. So the default for a built-in SQL function is to name the column whatever the function is. So if we were getting the average, this would come back as average. Since we're getting count, this comes back as count. But if you're getting this information back into your JavaScript to do something with it, count doesn't necessarily mean anything to you. You're like, what were you counting? Were you counting the number of songs that are longer than 4 minutes? Like, what were you counting? So we can alias by using as. And then we could say something like number of songs. And then when we run this, we see that our alias was used as the column name instead. Okay? And now this count kind of makes sense. because now we're getting back album name with number of songs. That's actually information that we can use, right? That makes sense to us. Okay, so I highly encourage you to alias fields. You can also alias fields that are ridiculously long to something that's much shorter if you want, if you don't want to have to keep typing something. Okay, so now that we've got our count here, why don't we throw in our friend the where clause and say num songs is, what did we want? That have more than 10 songs, where num songs is greater than 10. So we're saying take this alias and run it through here in a where clause. Where is our filter? That's what we know how to do. Execute. Syntax error. At or near where? Let's find out. So we'll take this off. We know that we don't want to touch this information because this is how our tables are joined together. We want to write everything we want to do down below that. You can think of this as giving you a massive record set. It's put the two tables together, and you've got all of the fields. So now we're saying where num songs is greater than 10, and group by albums.album name. Num songs does not exist. So, sorry? Well, it is actually created, but this is important about how SQL runs your code. Because it's declarative, but it does run in a certain order. And if we look at this, again, I included this link for you. So here's all of our different clauses and the order that we should be running them in. But here's the order of execution of SQL behind the scenes. So the first thing it does is it runs your from and your join. So it says from albums joined together with songs on this album ID, giving back all of the records, everything that was there. Okay? Then your where clause fires to filter that data down. So then where would fire. Then any group bys will group anything that passed the where. If you filter down with where, then your group by will collapse any records that match each other. Then we have this special having that shows up. Then your select fires. So as far as SQL is concerned, this line of code has not yet fired because it's waiting to put all of our records together, filter them, group them, and then from that, it will select the particular fields. So if you put something in here and you alias it, that's the it's not the very last step, but it's certainly not the first one. It's actually step 5. So you can't make reference to those aliases anywhere else in here. You can't make reference to them in the where, the group by, or the having because that line of code has not yet run. Okay? So if you see something like this where column num songs does not exist and you're trying to do this, that's what it's telling you. It's like the select hasn't run, you haven't created that yet. Okay. So what if we just cut out the middle person and we just run our count function again? We couldn't make reference to this alias, but can we count in here? Aggregate functions are not allowed inside of a where clause. That's fair. So what it's telling us is if you want to use the where, you have to compare a literal value. You have to say country equals Canada, age is greater than 18. You can't just say, I want you to count all of the songs. Okay? So where is not going to work for us. So there's a special where, another filter, that is used by group by. And it's called having. It takes the exact same, it's the exact same kind of arguments as where. It will filter our result set, but it can handle aggregate functions because it is actually part of the group by. So if we count songs.id and execute that, argument having must be type Boolean. Having count songs. It doesn't like that this doesn't actually match to anything. Kind of going off the rails here. Let's see if we have num songs. Oh, num songs doesn't exist. What am I forgetting to do? Compare it. So what did we say? We said we wanted greater than 10. right? It has to evaluate to a Boolean value, either true or false, in order to filter a record. We can't just say, having count of songs? What does that even mean? Wow. So there we go. So we selected a particular thing. We even threw in a num songs to show our count. Then we joined with songs. Then we grouped by album name. And then we filtered that group by. Okay? And just for clarity, you don't need to specify. The select and the having are two completely separate things. Okay? We can still filter our records. Select just says, what fields do you want to see from the record set? We still got back all of the albums that have more than 10 songs. We just can't see that because we got rid of that particular field. Okay? So this count and this count are two separate things. Okay? And as you saw, let's plug in num songs. Still, select has not yet fired, so we still have no access to that because we're inside of this group by. Okay? Execute that. There we go. Yes? Mm-hmm. Right. Right. Okay, so for Calgary, for clarification, there is no such thing as a falsy or a truthy value to SQL. It's either true or false. Okay? So it's not going to coerce things like JavaScript does, and it says, where you say if user input, and it's like, yeah, it's not an empty string or a zero, so it exists. That's not going to work for you. This is explicit. This is saying, give me back the count of the songs that are greater than 10. Okay, so this will evaluate to either true or false, not truthy or falsy. Okay, excellent question. Cool, and obviously we can go the other way. Which albums have songs less than 10? Which albums have songs that equal 11? Great. So you can do all of that stuff, but if you're using a group by, you have to use a having. Okay, it's completely separate to the where. And you could indeed have a where. We could strip off things from this if we wanted to pare down our record set before we crushed all of our records together. Maybe we only want to see certain albums. Maybe we only want to see certain artists, something like that. This is where our where would come in. We could say where artist equals Beyonce and then group by. And if we had more Beyonce albums, we'd have them all collapsed together and we'd be able to see this album had this many songs, this album had this many songs. Okay? So there is our having. Put that into here. Oh, they're getting harder now. List all albums in the database along with their songs, if any. Okay, so the astute among you will have noticed that albums has 5 records in it, right? But our previous query, having group by. This only gave us back 4, right? So we're not seeing 100% of our songs, right? We're not seeing list all albums in the database along with their songs, if any. So let's go back to the beginning. Select star from albums. Join songs on albums.id equals songs.album_id. If we look at this, we see that we have our first one, our second one, our third one, and our 5th one. Album ID 4 doesn't appear in this list. So which one of so this join is not working for us, this inner join, because we have an album that has no songs associated with it yet. So what kind of join do we need to have in order to see all of the records from table A, all of the records from our songs table? We need a left join. Cool. So if I go back up here, and we know that this was an inner join, right? Because if we execute that again, we see the exact same thing. If I change this to left, now we're seeing Homecoming all the way down. And down the bottom, we have our 5th album. but no song information associated with it. Because we said give us back all of our albums, regardless of whether they have songs. If they do have songs, show them to us. But otherwise, it just shows up down here as its own record. Okay? This ID is actually, because we weren't explicit, we got back all of the records from the albums table, which gave us an ID. But we also selected star implicitly from the songs table, which gave us back an ID, which overwrote the first ID. Because as you're probably familiar with like objects, if you said object at key equals this, if that previously had a value, it will be overwritten. So since we weren't explicit about what fields we got back, this ID is the songs ID. And so there are no songs associated with this, so there is no song ID. Okay? So let's see this. Let's add this to our group by. Let's see how that works. Where was our group by in here? Execute. So if we want to see, obviously this is an inner join. If we want to see everything from the albums table, now we see that we get that album and the number of songs is 0. Okay? So if you want all of the records from this table, regardless of whether they have associated records in the other table, left join is the way to go. And if you wanted to see this in reverse, all we have to do, albums, and we're grouping by, so we see left join, give us back that. Because from the songs perspective, and then right join gives us back the other side. So whichever one you have in your from is the A table. Whichever one you're joining to is the B table. So we've reversed left and right. There. So we've reversed those two. It doesn't matter. Write them in the order that makes sense to you. I usually do parent to child when I write my queries. That's why I did select albums, join songs. You can do it absolutely in reverse. You get back the exact same record set. Okay? So there's left and right join. So let me go back to here. Left join. There we go. So we said select from albums, left join songs, and then give us it back. Okay? So if you're missing some records, if you think that you should have some and they're not showing up, maybe throw a left in there. And you'll get back all of your songs. Okay? But this is not in particular what it was asking for. It was asking for this one. Nope. That's our group by. Oh, because we're counting. I don't want to actually count. I just want to select star. Select star from albums, left join, songs, execute. Okay, so there we go. And we see that we have our lonely album down here with no songs associated with it. Cool. Okay. Ooh, 13 minutes to get. We're getting down to our last two questions here. List albums along with their average song rating. So here we're using a new aggregate function, average. So we saw that from songs. Oh, actually, we can see it here. We see that each song has some kind of rating that I've associated with it. So we want to start with our basic query. Albums join songs. Okay. But we don't want the count of the songs. We want to use our new function, average, AVG. Again, because apparently that was too long to type out, right? Programmers lazy. So we're just going with AVG. But we have to pass it an argument. What do you want to average? We can't just say like we could with count, where we want to count them all. We have to give it some kind of numeric field, because how would you average artist name? What's the average of Beyonce and Jenny Lewis? Who knows? But if you said give me back the average of all the ratings, that actually makes sense. So we want to do songs.rating. Okay, let's see what happens. Ooh. What did the question specifically ask? List all albums along with their average song rating. So if we were going to build this up incrementally, let's get rid of our, oh, and we definitely don't want to save this as average. There we go, average rating. We get rid of this group by and fire this. This gives us back an average of all the fields, all the records in the table. So overall, I averaged it out to 3.54166666667. We see the float working for us here. Okay, but we want to see the particular albums, right? So that's where we would throw in our albums.album name. And there's where our must appear in a group by again, because this is an aggregate function. So that means we got to toss in our group by albums.album_name. And we can execute. Great. Can we add some other fields to this? Sure. What about albums.artist name? Execute. Oh, it got me again. I added a new thing to the select, but it didn't know how to squash the records on that. So let's make it happy. Artist name. So now we can see album, artist, and the average of each of the songs. Okay? So we can see that overall, I guess I was nicest to Ariana Grande. There you go. Make of that what you will. And we can pair this with other things, like is average rating less than or greater than 3.59. Oh, curses. Average rating doesn't exist. Again, because select is the last thing to run. So if we wanted to see this, we'd have to run that aggregation query again. And now we can see ones that are higher than 3.59. Let's go with 3.6. Why are you not filtering greater than 3.6? Oh, because it's rounding. Oh, it's order by. That's right. Thank you. What I was looking for was having. But you're right. Order by, there we go. So now we're ordering them by ascending. Let's order them by descending. Hey, 3.6. So I'm going to introduce you to one more clause before we get into our final select challenge. And this one is one that you will use to solve specific problems. Like, let's say I want to find out, someone asks you, give me back the #1 album in our database, the one with the highest average rating of their songs. Let's say we had hundreds of albums, but your boss says, I want to get back the #1 selling album, the #1 rated album. Well, how would we tell SQL? We know how to calculate the averages. We know how to look at them, but this isn't what the boss asked for. They don't want a spreadsheet that has all of the albums listed and all of the averages. They'd be like, this isn't what I asked for. I asked you for one value. So there's a clause that we tack on to the end called limit, and it limits how many records come back. So if we limit 1, it gives us back 1 record. If we limit 3, it gives us back 3 records. Okay? So if you have a massive data set and you just want to see an example of the data, then you could limit to 100, and you'd see like 100 records. They will come back in the order that you specify. So if you want the highest or the lowest one, order them, then limit by 1. Okay? So this gives us back the most popular one, the highest rated one. And if we said ascending instead, this will give us back the lowest rated one, but a singular value. Okay? So keep this in mind as you work through today. If it says I want a single value to come back from this query, just limit 1. Okay? Limit comes in handy. I have tables at my work that have hundreds of thousands of records, and they'll actually crash my browser if I did select star from. And I've done it. It actually overloads the browser. It's just too much. So if I'm looking at the latest data, I'll order by created at, descending, so I get the latest ones on top, and then I limit to 50 or 100. So I can see the 100 latest records that were created, and I can say, okay, that data looks good. Okay? So keep limit in mind. You will use it later. We didn't. All we wanted was all of the albums with their average rating. Cool. All right. We've got one last one. List albums and songs with rating higher than the album average. Okay. So this is going to utilize subqueries. Okay. So there's not any real way to prepare you for this. It's just going to look really weird. Okay. So we're going to say that we want songs dot song name. Okay, let's go songs dot song name. And presumably we want to get the average. Presumably. Songs dot song underscore name. And we learned about having, right? So if we said having average song is greater than songs dot rating, average song is less than song dot rating, songs dot rating must appear in the group by. Okay, songs dot rating. Query completed, but nothing came back. It seems like I'm barking up the wrong tree here. We must need something extra. We must need some kind of subquery. You'll use subqueries if you are comparing a table against itself. In other words, we need to run two queries against this table. One to give us back the average song rating, and one to compare each song against that average song rating, and then just filter down based on that, right? Okay. So let's get started up here with our subquery. Can't tab. There we go. So subqueries look very much like a regular query. We are going to average songs.rating from songs where songs.album underscore ID equals albums.id. Ungrouped column albums.id from the outer query. Okay. So clearly our grouping, let's see if we can get rid of this. Let's see what happens now. Ooh. Not bad. We're getting a little closer. We were able to get back some averages, and presumably it doesn't like that. Syntax error at or near select. Oh, comma. Okay. So now we can see the ratings of all of the songs compared to the averages. So far so good. We seem to be making progress. We're able to see the album average along with the particular rating. So if that's all we wanted, if you wanted for your interface, you wanted to be able to show every single song along with their ratings, along with the average album rating, there you go. This subquery would work. So what this is saying is give me back album name, name, song rating, and some other field where you're going to average the ratings together. And as we saw before, the default name is AVG, which doesn't really make any sense. So let's call that as song, let's go, average rating. There we go. So now we have average rating, but that's only 50% of what we wanted. List albums and songs with rating higher than the album average. Okay. So what did we do before? We had our we want to filter this down. We need to utilize a where, right? But we already know that we can't say where average rating is less than songs.rating. Missing from clause entry in table average. Oh, it's looking for table average. That didn't really work. What if we said, oh, that was average underscore rating. Let's try that. Column average rating doesn't exist. Remember, we're back in that where clause fires before the select. So as far as our query is concerned, this subquery never ran. What was our solution to that before? We pulled it, we just copied it and put it into the where clause, right? So let's copy this and put it into here. So now we're seeing that, and we could have reversed this. We could have said songs.rating is greater than this, but we're saying the average is less than songs.rating. And now we'll see that all of these are higher. All of the ones on the Beyonce album are higher than that average rating. This one has a 4, and we look down and we see that all of them conform to that rule. 3.5 is definitely higher than 3.44. Okay? If you wanted to see the ones that aren't bangers, as you kids say, right? Then you do it the other way. And then you see all the ones that aren't getting rated as well. 3.5 is less than 3.54, 3, 2, things like that. So again, this is a subquery, and you'll note that it's a bit cheaty, because if we take that and we just plug it in here, it says, I don't know what you want. You haven't specified how we're joining these two together. You said, give me back the average from songs, but then what is this thing? There's no join, there's no anything else. So in a subquery, it actually takes advantage of the join specified in the outer query, okay? So that's why it looks like a truncated select statement. But essentially what we're doing is we're running 3 select statements all at the same time. We have our outer one that will fire last. Then we have this inner one that gives us back an average rating, right? And then we have this one down here. And what did we say before? Select is just about display. So this runs just as well, and you'll see that we're getting back the right values. The only reason we would specify this subquery in the select is if we want to see that average rating. But we know that this ran and it filtered everything for us. Okay? So those are, and I'll put this back to how it was. There we go. Make sure that's still running. Awesome. So that was our very last one. And again, this is something that you'll use very seldom, and it's only used if you want to compare a table to itself. Okay? How are we doing for time? 12:01. Perfect. Any questions about what you've seen so far? There's one more thing that I want to show you that you might come up against today. And for that, we're going to move back to the users table. And that is, so let's say we want to select country. Let's say the marketing department sends us an email and says, I want to see all of the countries that we have users in because we want to narrow our advertising. We want to focus our marketing in the countries where we have customers, or perhaps conversely, in the countries that we don't have customers yet. So you're like, well, great. I'll select country from users and send that back to marketing. Well, they'll probably want it ordered, perhaps, right? Because we like to see things in order. So let's order by country. Let's run that. Is marketing going to be happy with us? No. Exactly, you're skipping ahead. But they're gonna email us back and say, why did Afghanistan appear like 50 times in your, what am I supposed to do with these? You sent me 10,000 lines. Well, we're gonna introduce you to distinct, which says, give me back only the distinct values from this column. If Afghanistan appears 40 times, I only want to see it 1 time. So if you call distinct on a column, then you only get back the distinct values from that. So we see that we have each country only appears 1 time. And this is the list that marketing would be looking for, right? This tells them we have users from all of these countries. Okay? We can do the same thing if we jump into albums. Although this would be more arbitrary. Select distinct rating from songs, if I spelled distinct correctly. Now we just get back the individual ratings. Like presumably 3 appears more than once. Let's order by rating. There we go. 2, 2.5, 3, 3.5.5. But if we run distinct, we only get back the distinct ones. We only get back 1 instance of each one. Okay? So this is another one that you'll use if you're asked to retrieve specific. I just want to see 1 instance of each country in our users table. I want to see 1 instance of each rating, something like that. think about distinct. Okay? Any questions before I let you go? I will include all these links that I've been using today in the notes. Anything? Calgary? All good? Everybody in Vancouver good? Awesome. Ready to start an entire day of writing nothing but select statements? Yeah. Awesome. Cool. Thank you very much.